The last speaker of this conference would like to point out that this afternoon there will be lectures by Sir and Benjatesh in this room, but perhaps they are organized by graduate students and postdocs, so maybe they will be aimed at to the younger audience. But anyway.
But are we all Sarah's postdocs?
Just okay. Maybe you should be aware of these lectures. Okay.
It's aimed at graduate students.
Okay. 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 I'm very happy to present Dan Abramovich, who will be talking about his joint work with Tëmkin and Włodarczyk on the resolution on singularities in characteristic zero using weighted blow-up.
I thank you all for coming on this last day with hot weather. I thank the organizers for inviting me to give a lecture in this wonderful city. And I should say, as a last speaker, I have the honor of thanking in the name of all the participants, the organizers of this workshop, Björn and Alexei. Am I missing somebody? For arranging for such a string of inspiring lectures throughout the week. So may I call on you? This is about embedded resolution of singularities. It's joint work with Michael Tëmkin from Jerusalem and Jarosław Włodarczyk from Purdue. There is parallel work that you might have seen on the same day on the archive by McQuillan and Marzo. And I apologize that there's nothing here about rational points or necessarily irrational varieties. Maybe the one analogy is that in both subjects there are difficult theorems that need to be looked at again. And also very difficult open problems. Let's start. Embedded resolution, if we have a curve, let's say embedded in a smooth surface, how do we resolve it? Well, we see in Hartshorne, to resolve a singular curve, you find a singular point, no matter which one it is, you blow it up and something gets better. You read in Hartshorne that the arithmetic genus gets slower and therefore it's going to stop. And that's what we want to mimic in arbitrary dimension. But surfaces and higher dimensional varieties are more complex. And so we have to think about, so what you want to do to resolve a singular surface is you want to find the worst singular locus of the surface, show that that worst singular locus is smooth, and you want to blow it up. And unfortunately, this in general does not get better. This deserves an example, the example that you may have seen in your elementary algebraic geometry course. You consider the Whitney umbrella. And being a geometer, I'm required to draw a picture. So here's the Whitney umbrella. And if you want some shading, we can. This is supposed to be red, and this is supposed to be white. Okay, here's the Whitney umbrella. Where is its worst singular point? It's right here. The point called the pinch point is a worst singular point, and that's what you want to blow up. So let's do that. Here's an actual professionally produced image. by Eleonore Faber. Where singularity is the origin, and you blow up the origin, namely the ideal x, y, z. Nothing really interesting happens in x or y. It immediately gets a little better. But in the z coordinate, let's see what we have in the third. So x3 just means I'm in the third chart. So I'm pulling out z from x and from y, and I get new variables x3 and y3, and I'm plugging in for x3 times z, and so x squared becomes x3 squared z squared, y squared z becomes y3 squared z squared times z. So here we go. And I pull out z squared because in the z coordinate chart, this is the exceptional. Okay, the first term is exceptional, and the second term is what you started with. So nothing got better. And you wonder what is going on. Does this variety refuse to be resolved? Is it going to sue you for mathematical malpractice if you continue like that? So what people usually do is continue by brute force. There are techniques to do that. So I'm not saying that it's impossible to resolve surfaces, but that's not what my goal is here. So here's the main result, which says that nevertheless, you can do what I set out to do. This is the theorem that Tëmkin, Włodarczyk, and I proved, a parallel theorem by McQuillan and Marzo. I call it weighted Hironaka. It's weaker than Hironaka's theorem. And I apologize. I have to require characteristic 0. And if you wish, we can discuss why. I'm saying there is a procedure. I need to define the red words. There's a procedure f associating to a singular variety, singular subvariety, embedded, so x, embedded in pure codimension in a smooth variety, a center, which I call J bar, with associated blowing up, which I called y prime, and proper transform of the original variety x prime, such that the maximal invariant of x prime drops, is smaller than the maximal invariant of the original, maximal singularity invariant of x. In particular, this invariant will lie in a well-ordered set. So after some number of applications, the resulting variety will be smooth. Okay? You'll see what J bar is. So I'll have to define what a center is. I'll have to define what blowing up of a center is. Everything is slightly different from what you're familiar with, but not much different. So the first word I want to explain is procedure, and procedure just means a functor in the category of varieties with smooth surjective morphism. If I have a morphism y1 to y, and the resolution procedure gave me y prime, the resolution step procedure gave me y prime, then a resolution step procedure of y1 will give me, well, I'll call it y1 prime, where a y1 prime is simply the pullback, under the assumption that the morphism is smooth and surjective. This in particular implies that you never do anything to the smooth locus, because the smooth locus is basically pulled back from a point. I'm a little bit cheating here, but
the procedure is not local, like you need to require surjective for the smooth.
so the one-step procedure cannot be functorial for smooth morphism, because when you move to the smooth locus of the original x, you're going to do nothing. Okay, so as a procedure, it's not the same. You're doing less on an open set than on a big set. So you can reinterpret the final result as a functor on smooth morphisms without surjectivity.
Is your final resolution as a morphism over a smooth morphism?
Yeah.
The functor, you mean, what is the input object?
The input object is a pair.
It's the
X and the Y. Yeah. I mean, in truth, we actually work with an ideal inside OY, but we'll get there.
Okay, so then a morphism is then we have the smooth projected and the inverse image of X?
The proper transform of X. That's what I define here. I define X prime to be the proper transform of X. I remove the exceptional part.
No, but a morphism in the input category.
The more, yeah. What, I'm sorry. So it's, yeah, so this is Cartesian, and then you look at the, oh, if you, I mean,
There's no X in that.
okay, so that's because I was lazy. There's an X, there's an X prime here, and X1 prime will be just the inverse image. There are other questions you are welcome to ask. This is a foreign subject to this conference, so I realize that I have to explain things. So I have to tell you things about invariants, centers, blowings up, and maybe I'll get to some proofs also. So I want to look at invariants and look at them in some examples. So the invariants will define for every point in X, we define an invariant in sub P of X, which lies inside a well-ordered subset of sequences of integers of length up to the dimension of Y. And we show that this invariant is lexicographically upper semi-continuous and point is smooth even only if the invariant gets the minimal value. So I know when to stop. We define the maximum invariant that I alluded to in the previous slide. It's just the maximal value over all points of the invariant of the points.
Depends on X.
Again?
Gamma depends on X.
Gamma, it depends on, basically on, you can make it totally independent of anything with some agreement what you do when you raise the dimension. It maybe depends on the dimension of Y, the way I set it up. It's just a subset, a well-ordered subset of this set of all sequences, not of integers, but of rational numbers. Let's look at the Whitney umbrella. The way I'll define the invariant will be the following. I first look at the lowest degree monomial that appears in any presentation of this singularity. The lowest degree is 2. The order of vanishing is 2. And then I look at, in essence, I look at the next possible values. In this case, Y and Z appear in monomials of degree 3, so I have 2 occurrences of the number 3. And we'll make it a little bit more formal in a few minutes. How am I doing with time? Okay. I want to remark that this invariant is not at all new. So first of all, this invariant, as written, Michael and Jarek and I used in a previous paper as written. But in fact, it appears in all the great previous work of Beerson and Millman, Villamayor, and Sinas Villamayor, but it appears interspersed with other data. So somehow we missed it. But it was there for at least 30 years.
So sorry, Dan, just on the previous slide, that P is the pinch point, so it's that
I'm looking at the worst singularity of the Whitney umbrella, okay, namely the origin. And I'm saying at the origin, the invariant is 2, 3, 3, because visibly those are the degrees where things appear. I will have to explain what you do when it's not visibly the case. Here's a preview of what a center of blowup will look like. If the invariant is at P happens to be the maximal invariant of X, then I'll define a center according to the invariant at P I'll define the center according to the invariant A1 through AK. And locally, at any point which admits that invariant, the center will look like X1 to the A1 all the way through XK to the AK. So notice that the AK are rational numbers. So you have to ask, am I pulling your leg? I am going to massage this center a little bit. If I pull out an integer out of the sequence A1 through AK, and I pull out an integer not so that the result is integers, but it's inverses of integers. Okay, so I make it so that this is L times a sequence of inverses of integers, and let's normalize so that their GCD is 1. Then I define the reduced center to be what I get when I write the same thing with the WI in the denominators. Okay, I'm just formally taking the Lth root of J. So take the formal Lth root of J, and this is J bar, which tells you that I'd better tell you at some point what on earth is J. Here's what you have in the example. Well, the invariant was defined using the monomials that I saw in front of me. So I'll just put J as x squared, y cubed, and z cubed. And since in order to make these inverses of integers, I need to pull out 6, then the reduced center will be x to the 1/3, y to the 1/2, and z to the 1/2. And I want to remark that even this has been staring in our face for a while, and we have been looking how far it went. And there's a published work by Boris Yusin from 1991, which I believe he actually completed in, maybe 1990, which I believe he completed a year before. So it's 20 years, no, it's 30 years old, right? Yeah. Where the same kind of thing appears in a slightly different guise. It's written in terms of Newton polyhedra.
Do you mean J bar?
Say again?
Do you mean J or J bar in the last?
J appears. So J is the thing that you measure things against, and J bar is what you use to blow up. Okay. So there are a lot of things I need to explain. And maybe first, before I explain the formalism, I'll tell you what you do with the Whitney umbrella. So as you will see, the blowing up of the reduced center makes the reduced center a principal ideal, not center, but actual ideal. And explicitly, this is obtained by, well, 3 charts. So the important chart is going to be the Z chart again, because nothing interesting happens at the X and Y charts. So on the Z chart, I need to take a square root of Z. I'm putting Z, so to speak, in degree 2 to make a weighted blowup. So I need to take a square root of Z and pull that out as much as I can from the other variables. So since I allow one cube of x, then I'll pull out w cubed out of x, out of x. I'll pull out w squared because of the 2 out of y. And as I said, z is getting its square root. The chart then is just a spectrum of the polynomial ring with these variables, w replacing z and x3 and y3, with the action of plus or minus 1 because I took a square root of w. So what I get in the blow-up is not a scheme. It's going to be an algebraic stack. That's a natural way to do a weighted blow-up. So, yeah, some people agree with me here. The action of plus or minus 1 is given by the natural action. So w is multiplied by minus 1. Y3 remains invariant because I'm pulling w squared, but x3 is not remaining invariant because I'm pulling out w cubed. Let's see what happens on this chart to the original equation, x squared equals y squared z. Well, I'm plugging in w cubed x3 for x, and I'm plugging in w squared y3 for y, and here's what I get.
Sorry, then is it basically a definition of the blow-up?
This is I will give you a definition of the blow-up in a bit. I'm giving an example as much as I can so as not to force resolution of singularities on people who work on other hard problems, okay? So this is what you get. You just plug in, and this is what you get. You can pull out w to the 6th. And notice that here, instead of having a z, because we were careful to choose the weights correctly, we only have the y squared. So again, the proper transform is just this part. And if you think about the degrees of monomial appearing here, they are 2 and 2. And no matter how you think about ordering sequences of rational numbers, it had better be the case that 2, 2 is smaller than 2, 3, 3. Okay, so something immediately got better. Tatiana, yeah?
Here you have 2 irreducible components. You have to take one of them.
No, I don't. So you're worried about the word variety that I used in the beginning. For this lecture, varieties is un schéma absolument réduit de type fini sur un corps. Okay? And it doesn't need to be even separated, okay? It's not a nice variety in the sense of this program. Speak up.
Later do the inductive step, do you need to actually formulate everything for stacks right away? Or?
Yeah, so this suggests that I need to extend my theorem for stacks. However, the theorem is functorial for smooth morphisms. So I don't. It's well, maybe I'll come back to it later. One of Jarek's revolutionary ideas was that thinking about the resolution of singularities functorially makes it easier. So if you aim to prove resolution functorially, then a lot of trouble gets away, disappears. All right. So I asked you before, what was going on with that variety? Did it not want to be resolved? And for 20 years, Bernard Tessier has been telling us to resolve a variety, you should approach it politely and patiently and ask it how it wants to be resolved. And listen carefully. And indeed, if you listen carefully, this is the way this variety always wanted to be blown up. There are birational geometers who knew that All along, it's just that we lacked the language to do it in general. I'm paraphrasing Bernard. He actually has an advice that is vastly more, more radical, but this suffices for me.
Can I ask a question?
Yes?
So where does the action on the x order come from? Because otherwise, this is not going to be birationally equivalent with the thing you have, right?
The quotient under plus or minus 1 is isomorphic away from the exceptional locus to the original, to the appropriate chart of the original variety. So yes, it is birational, but no longer a variety. The stack-theoretic quotient is birational, proper and birational over the original variety.
But what in your procedure told you that you have to act?
I can't.
What in your procedure told you that you have to act on the x coordinate like that?
Why am I acting on x by minus 1? Because not on x, on x3. So the original variables are invariant. I took a square root of z, and therefore the action on the square root is by plus or minus 1. I pull out the square of w here, so the action is by zeta squared, minus 1 squared. And I pull out a cube here, and the action is by zeta cubed, namely minus 1 cubed. I'll remember this, it will come back. So I need to tell you things slightly more formally, if you wish. Yes?
How did the Hironaka or Zariski or the ancients resolve the singularity? What did they do?
What they were doing is they resorted to violence. So what they realized that it's worthwhile remembering the exceptional divisor, and what is changing with the Whitney umbrella when you blow up is suddenly there is an exceptional divisor, and the exceptional divisor tells you that something is better, namely you have a choice of a distinguished variable, except that it messes up the rest of the algorithm. So they had to do a further what one calls the monomial stage of the algorithm. So I want to save you that trouble. More questions? I want to define for you what is the blow-up in a slightly more formal way. So suppose I'm given the center, which I still have to tell you what it is. For the time being, think of it as a collection of local parameters, of regular parameters, with a collection of integers w1 through wk. I look at Hartshorne, how a blow-up is defined, and I just change where I put the variables, except that I need to take integral closure. So if I send yi to, not to xi times t, but to xi times t to the wi, I'm putting xi in degree wi, and unfortunately I need to take integral closure. I get a subalgebra of the very simple algebra Oy of t. And I'm taking the stack-theoretic blow-up associated to that algebra. When you have a graded algebra, okay, so there's a group here who have been doing these things. If you, inside the spectrum of the algebra, there is a vertex, namely the vanishing locus of the irrelevant ideal a la Hartshorne. And you define the blow-up or the proj of the algebra to be the spectrum of the algebra, remove the vertex, and take the quotient just like you do always, but in the stack-theoretic sense. That's the only difference. So you systematically use the fact that you have a good way of talking about quotients in the theory of stacks.
Why do you need to take integral closure?
Because this is not the right thing in general. So for instance, if the wi are all divisible by m, then I'm getting something that is not, then I'm getting the wrong scheme, in fact.
Supposed to be co-prime, right?
Say again?
You scale them to be co-prime.
In the previous case, I insisted that they are co-prime, but in fact, in the proof, I need to also consider the case that they are not co-prime. But even if you are not in the, yeah, I mean, it's in general not going to be integrally closed. So for instance, xi times t is in the integral closure. Yeah, there we go. So as always with the blow-up, it's worthwhile looking at charts. So you're taking proj. There are charts for each of the generators being invertible, and you think about it a bit, and this is what you get. This is an old description that you can find in work of Miles Reed, and you can find in work of, well, okay, so I learned it from Miles Reed, but it's probably much more ancient than that. So I'll tell you just what the x1 chart is, because all the charts look similar up to permutation. So x is replaced by a variable u, and all the other x's are replaced by xi prime. There will be an action of the roots of unity of order w1, because I'll take a w first root of x. So here we go. x1 is u to the w1. And for those variables that appear in the center, I'll write xi equals u wi xi prime. The other variables remain as they were before, just like in the usual blow-up. Stop me if I'm going too fast. So that's just a spectrum of a polynomial algebra. I'm modding out in the stack-theoretic sense by a group of root of unity. That's actually an innocuous type of stack structure. I just need to tell you what the structure is, and it is imposed on us by the fact that the original xi are invariant, and u is acted by a primitive root of unity. So u is acted by a primitive root of unity. x2 prime, or xi prime, is xi divided by u to the wi, so the character is zeta to the minus wi. Every number theorist knows how to deal with this, so I hope we are okay with that. I left some space for something that maybe David will warm up to, but I don't think this is the right audience. There's a way to do this with toric stacks.
So the fiber is a weighted projective space?
Is a stacky weighted projective space. The exceptional locus is a stacky weighted projective space. Or I should say this: the exceptional locus. I mean, only k variables appear, so it's a weighted projective space bundle over n minus k dimensional smooth space. Is that right? Yeah. Yeah, the other variables, x, k plus 1 through xn, remain the same. Just like with usual blow-up. I mean, this is not necessarily an isolated singularity, so I have to blow up higher dimensional loci. I have to tell you how to define J from the, even before I tell you what J is, I have to tell you how to define J. And here's how you do it. This is a procedure that has been done many times in the past. We were not, our eyes were not open to the fact that you can put together a resolution procedure out of that until now. So we consider, I'm changing the example because the Whitney umbrella has given me all that it can. I've been rained on, and poor Whitney was not very successful protecting himself from the rain, but this was useful. But now I need to use another example. I'm choosing an example with y to the 8, and here I drew the Newton diagram of the monomials that appear. I put y to the 7th as an option for another example. As you can imagine, I'm not really working with x itself, but I'm working with its ideal, as you have seen. So the ideal generated is what I care about. Look at the order so the point is the origin. Look at the order of the point of the order of vanishing of the ideal, namely what is the degree of the minimal degree of a monomial appearing, and evidently it's 5. And now I need to choose a regular parameter, and I choose the regular parameter to be any parameter appearing in such a monomial of degree 5. In this case, there's only one monomial of degree 5, namely x to the 5. So my only option in this case is x. Which means that the beginning of my center will be x to the 5. I need to choose what to do in the next one, and I need to choose another regular parameter. Y will work, actually.
Doesn't that hurt functoriality?
Say again?
Doesn't that hurt functoriality?
Okay, as is pointed out here, I'm making a choice. So I will list towards the end of my slides, there will be a list of theorems to be proven, and we'll see what I have time to do. But yes, I'm making a choice, and this is I'm violating my goal, it seems, but I have to show that, in fact, this is not the case. So even in this case, I could, instead of choosing x, I could choose x plus y cubed. That would work. In this case, the center will look like x to the 5 and some power of y, and I need to choose which power of y. And I need to look at the various monomials that appear here. One monomial that appears is y to the 8. It turns out that 8 here is a very large number. So the other monomial is what I care about. And this is important because x also appears in that monomial, so I have to play them against each other. So I need to balance the original x to the 5 with this monomial. Balance means basically draw the straight line on the Newton diagram and see where it meets the y, the powers of y axis. And it meets precisely at 15/2. So I should write here in some color, not chosen yet. Maybe white will work. No, it's blue actually. Okay, somewhere between 7 and 8. Since 15/2 lands below the 8, it is more important than the 8. And therefore, the center will be x to the 5, y to the 15/2. And I mean, you can read from the weights that I used here, or compute directly from this, that the j bar is x to the 1/3, y to the 1/2.
But if that line is not above y to the 8th, would you just put y to the 8th? You would have balanced.
This is the next example.
Ah, okay, sorry.
Thank you. So Jordan asked what would happen if the line landed above. Well, the line does land above y to the 7. So if I started with the equation is y to the 7, then since 7 is less than 15/2, the invariant I would use would be the one associated to this line from here to here, which I drew, which I indicated here. And the associated reduced center would look like this. Okay, so that's just a procedure for the time being. Ooh. So let's see how the blow-up looks. Considering the first one, I'm blowing up, remember I'm blowing up let's just write it so that we don't forget. X to the 1/3, y to the 1/2, with in parentheses, this is J bar. So this means in the X chart, X is U cubed, Y is U squared Y1, and this is the equation that I get. I calculated that at home. I actually checked it many times because I always make mistakes. And it does come out as U to the 15th, so I have a 15th power of the exceptional variable. And this turns out to be smooth. Easily checked. It's usually not the case that you immediately get something smooth. And I also calculated for you the Y chart. Again, it happens to be smooth. So that's the example. I also calculated the examples of the other one. They are equally uninteresting. The interesting thing I wanted to give with this example is the fact that the invariant can have rational numbers. The 15/2 that I got here. I have to tell you how to do this in general. And how to do this in general requires a technique that is an ancient technique from a resolution of singularities, 25 years old. Once you choose the first variable, you want to restrict something to the vanishing locus of the first variable. But as we saw here, it's not enough to restrict the original ideal, because then we would just get to y to the 8th. That's no good. You need to have some information from the actual monomials that dominated in this case. In this case, it was x cubed, y cubed. Yes? So to reach those monomials, I look at derivatives of the ideal. So I'm taking the original ideal, and I'm taking various derivatives. And I thought I might, indicate how this is done. So I'm again working inside, I'm defining an algebra inside maybe A1, inside OY of t. And its first term is, its zeroth term is OY. And then in degree A, I'll put the ideal I instead of OY, I times t to the A. And in degree A minus 1, I'll put DI and degree, etc. Say again? So for at this step I could use Hasse derivatives. The next step is where I would fail. So I define the coefficient ideal to be what I get in a degree that everything, all the information that I need comes in. Being lazy, I'll just take the degree A factorial part. And I call that the coefficient ideal of I in the corresponding to order A. I wrote here what it means formally, but you don't need to worry about it. It's just what you get from this by generating from this an algebra. This, as it is, it's not an algebra. It generates an algebra. What you get in degree A factorial is CAI. So you just run over all monomials of the correct weighted degree. Namely, the degree has to be at least A1 factorial. This is the ideal I restrict to x1. I define I2 to be the restriction of the coefficient ideal to x1 equals 0. And now I can define for you the center associated to an ideal. Suppose A1 is the order of the ideal with x1 a regular element in. So the way here's where characteristic comes in. because I'm in characteristic 0 and because dA1I, because I is of the order A1, dA1I is the unit ideal, then there must be an element whose first derivative is 1, namely a regular element, in characteristic 0. In the previous derivative of I, there must be an element whose first derivative, there must be an antiderivative in dA minus 1 of I. This is called maximal contact, and this is where characteristic 0 is important. And now you use induction. Suppose I2, the lower dimensional thing, has invariant, which I call inv p I2, defined using parameters x2 bar through xk bar. I choose arbitrary lift, so I'm violating functoriality again. I choose arbitrary lift of what I have in one lower dimension. And I define the invariant to be the concatenation of A1 with the invariant of the I2, except I need to remember that I raised the degrees from A1 to A1 factorial. So there's a factor of A1 factorial divided by A1 that I have to rescale. So that's what's written here. And I call this my center, which I still have to tell you what on earth it is. And in our latest example, you just calculate the coefficient ideal. The coefficient ideal in this case has to be principal because modulo x, well, okay, so the restricted coefficient has to be principal, and it's just y to the 180. So x to the 5, y to the power 180 divided by 5 minus 1 factorial is this. It's even easier in the case where you have a 7 because then you don't get a rational number. Questions? I of 2 was the restriction of the coefficient ideal to x1 equals 0. And it suggests that there's an induction here. I mean, of course, the invariant of I of 2 is defined using its coefficient ideal, etc. So I have to tell you what J is. And this is where a new formalism is required, but not so new. This is stuff that people in birational geometry essentially have been using. So I want to consider ideals on all possible blow-ups of x, and I want to use also rational coefficients. Since every ideal becomes principal after some blow-up, then I mean, namely you blow up that ideal, then you might as well look at just principal ideals, and you want to work on the limit of all blow-ups, so that's what's known as the Zariski-Riemann space of the variety y. So consider the Zariski-Riemann space of y, which is the limit of all blow-ups. It has a sheaf of ordered groups gamma because every point corresponds to a valuation on the original y. It has an associative of rational ordered group gamma tensor q, and a valuative q ideal on y is a global section of gamma q positive, the positive part, the positive submonoid of the sheaf of ordered groups. In essence, this is the monoid of Cartier divisors on the Zariski-Riemann space, because the groups are quotients of the fraction field, so locally, every such thing is given by the Cartier divisor associated to a function. To a valuative Q ideal, you can associate an ideal approximating it, namely, you can look at all the functions whose valuation at any point of the Zariski-Riemann space is at least a given one. And vice versa, if you have an ideal, everything here is Noetherian, so an ideal is finitely generated. I can take the minimum value of finitely many elements of my ideal at any given v, and that gives me a evaluative Q ideal. So there's a way to go back and forth. One thing it does is if you have two ideals which are whose integral closure agrees, then they become the same thing here. But this also allows you to take things with rational coefficients, and then integral closure doesn't really mean anything. So in particular, a center is evaluative Q ideal. It is evaluative Q ideal locally given by the type of equations I gave you. One technique that has been used in the last 20 years in resolution singularity is admissibility of centers. You only allow yourself to blow up things that lie inside the highest singularity locus of your given ideal. So you say that a center is I admissible if the associated evaluative Q ideal as a section of the ordered group is less than the evaluative Q ideal associated to I. If you think about as ideal as ideals on the Zariski-Riemann space, the inclusion is reversed, but then as zero set. So this just says that in some sense the zero set of J is contained in the zero set of I in a suitable strong sense. There's a little lemma that says that because I define for you a blow-up, you can check whether or not J is admissible by seeing what happens on the blow-up. So on the blow-up, admissibility just means that I can pull out the exceptional to the right order, and what I have remaining is really, so the exceptional is an ideal, e to the L is also an ideal, so what I have remaining is in general a fractional ideal, but the admissibility just means that when I pull out I just get an ideal, not a fractional ideal. And the connection with coefficient ideals is that you can test whether a center is admissible by looking at the coefficient ideal. So a center is admissible for I if and only if the correct rescaling of it is admissible for the coefficient ideal.
All the AIs are less than P. You could do in characteristic P, you could do the job, right?
Yes, but this is rare. Just think about the Whitney umbrella in characteristic 2. So all I said about the Whitney umbrella is correct in characteristic different from 2. So here are the key theorems. I have 8 minutes. I don't know how much I can prove of those theorems, but I have to show that the invariant, which I define using various choices, is this still working? I define using various choices, is well defined, upper semi-continuous, and functorial. I have to show that not just the invariant is well defined, but the center is well defined. I have to show that the center that I define for you is actually admissible, so I can blow, when I'm allowed to blow it up and pull out the correct power of the exceptional ideal and get a new ideal. The final result, I break into two pieces. The invariant of the transformed coefficient ideal, if I write the coefficient ideal times the pullback of the coefficient ideal as pull out as much as of the exceptional as I should, and I write the C prime for the remaining ideal, I need to show you that the invariant of that dropped, and from that one shows that the invariant of the original ideal also dropped. So these are the main theorems that are required. I have 6 minutes. I mean, what my slides have is just this. But I'm here open to requests and suggestions, what you want to learn. Because this is not number theory, so.
We have plenty of time for questions.
Can we hear you, actually?
Yes?
Okay.
Okay, maybe I just go to Michael.
He's the leader. I cannot overrule him.
So what goes wrong if you just try applying this procedure in characteristic P?
All right. How do I bring it up? Yeah, so yeah, in characteristic 2, it doesn't matter if it's a plus or a minus. So I want to take, so I know that the order is 2, so if you take the full ring of differential operators so the full module of differential operators of degree up to 2 applied to I, then you get the unit ideal, because I'm allowing the fancy derivative for x squared. But I don't, what I need is something, so what is di? I don't have an element of order 1 here. In characteristic 0, I would have an order 1, an element of order 1. I mean, what I'm missing here is 2x, right? There's also 2yz, right? But, so I don't have this, because 2 is 0. And that is what goes wrong in this procedure. Of course, this tells you that you want to do, something else. You want to blow up x comma y, which in any characteristic actually resolves the singularity, but this is not known to be part of a procedure for resolution in general. And if you come up with such, then you'll be famous. Oh, the question was there. Okay.
So
Antoine.
after one step of the procedure, you have a stack.
After one step of the procedure, you have a stack. Yeah.
So you've probably hidden under the rug that you need to do everything for stacks. And
So,
at the end, once you have a stack, and people like us want to have a variety. So
yes. So what Chambert is asking is what to do with the stack that you get at the end. So I started with x, and I blew up many, many times, and I got xn, which is non-singular, but it is going to be a stack. In the procedure, because I'm working functorially, I don't need to put an input which is a stack, because the procedure is functorial. But the result will be a stack. And then you can, okay, there are two things you can do. If you are optimistic, then you look at it and you carefully realize that this has only abelian quotient singularities, so for many people this is good enough. But for many people it's not. And there's something called Berg's destackification. which gives us a procedure of further totally combinatorial blowing up of the stack in such a way that the passage from, so this is again smooth, so these are just what they call stacky blowups. In such a way that this is also, this is just a composition. The passage to the coarse moduli space is a composition of root constructions, so this is also smooth. So this is actually a resolution, functorial for smooth morphisms in the old sense, in the Hironaka sense.
Okay, more questions? No? Maybe you could pass the microphone too.
Yeah, the people here don't seem to have a chance, but we have time.
So one of the choices you made, I guess, is the order of the variables. So in that picture, if you started with y, I guess you would have looked at the other line from the monomial y to the 8 to, I forgot exactly what it was because it's written a little smaller. So those two lines make up the lower convex hull of the monomials. If there were more monomials, could you take any edge of the lower convex hull?
So the procedure, the way I worked it out, does not allow that. In essence, what happens when you, in essence, what you do is you look at the first step is to look at the Newton diagram, not of the ideal, but of the coefficient ideal, and that does some homogenization. So it throws into the equations all monomials of degree 5. So y to the 5, sorry. No, I'm messing up. Sorry. In this case, no. In this case, I misspoke. In this case, the coefficient ideal will also have this monomial here. Is it this one? This one. And right. So it really forces you to take this minimal. So okay. So the first thing you take is the minimal order. So the minimal order is 5. You are not allowed to start with 8. And then you look at the relevant phase that contains this. Okay, and you go from there. It's a bit more complicated if you don't have something on the edge. If you start with x1, x2 plus x2 cubed, the procedure actually tells you to take both x1 and x2 with degree 2 and ignore this entirely. So it's given by the Newton polyhedron, but not totally directly.
Any more questions, please?
Does this work?
Yes, it does.
You mentioned there's another preprint and another group of people who obtained similar results. What are the differences between the two approaches?
So my understanding is that two differences. So McQuillan, with his student Marzo, worked out systematically with Newton polyhedra rather than centers. So they have a different, they use a different foundation, so to speak. That's right. They use Newton polyhedra and just define things using the Newton polyhedra, very much like in Yusin's paper from the 90s. The other thing is that they go ahead and they prove things. I mean, I worked with varieties just because it's convenient, but you can see that I didn't use much, so if I understand correctly, they proved it in the correct generality of Chi schemes.
Any further questions?
For characteristic P, what about if your scheme has, let's say, a lift to something flat over the vid vectors. Could you work with vid vectors instead and then reduce?
This has a lift.
It does, yeah, indeed. Yeah. But
So what I do in characteristic 0 doesn't really help me.
Okay, but the terms are non-zero, like your 2x becomes non-zero if you work mod 8, let's say. It's in some ideal which is small.
So
yeah.
Try it. Blow up 2x. Yeah. This was here a moment ago. Yeah, so
at least it's not non-zero, so you have something very little, but you do have something.
It doesn't work so beautifully. So this calls you to blow up xy2, if I'm not mistaken.
Yeah, I think so. Yeah.
And xy2 gives you a blow up that doesn't improve things. So I haven't figured out how to proceed from that.
Okay. Thank you.
I should say, when you have some new idea or new method, you have to try. But this problem is evil, and it's especially evil for people who have tried it before. So it takes somebody new to come in and take it by surprise. So please.
Okay, maybe we stop here and thanks for all the questions, and thanks to Dan again.